Continuing on with the Chapter 10 lecture series, we're now going to be moving on to discuss infrared spectroscopy. So infrared spectroscopy is a really useful tool primarily to identify the major functional groups in a molecule. Infrared spectroscopy measures the absorbance of light in the 2500 to 25,000 nanometer range. Compared to ultraviolet spectroscopy or UV spectroscopy, which focuses on electronic energy levels, infrared spectroscopy focuses on transitions in vibrational energy levels. So for example, if we're taking a look at the energy levels, we have the electronic energy levels, and within each electronic energy level, there are more finely divided vibrational energy levels. Infrared spectroscopy focuses on transitions between these vibrational energy levels. So what are vibrational energy levels? Vibrational energy levels correspond to unique modes of bond bending, stretching, and twisting. Each mode of bond bending, stretching, and twisting has a unique energy. Here are some examples of bond bending, stretching, and twisting, such as symmetric stretching, asymmetric stretching, and in-plane bending. Molecules with a given bond will absorb light of a specific wavelength, frequency, and energy corresponding to the energy required to transition between vibrational energy states. The key point of infrared spectroscopy is that we can observe unique functional groups based on the frequency of light that they absorb. So for example, a carbonyl group will absorb light of a very specific frequency, and that will cause the carbonyl group to transition to a higher energy vibrational state. The carbonyl group can absorb light of a specific frequency and begin to start to stretch and move as part of that higher energy vibrational state. So what that means is if your molecule has a carbonyl, it will absorb light of a defined frequency. And we can use the fact that this compound absorbs light of a specific frequency corresponding to a carbonyl's absorbance frequency to in turn determine and assign the fact that this compound does in fact have a carbonyl. So we can measure how a compound absorbs light and measure the frequency of light absorbed, and we can use that to assign and determine what functional groups are present in our compound. And the reason why this works is specific bonds absorb specific wavelengths and frequency of light, and that causes those bonds to transition to higher energy, vibrational energy levels. The bond will bend, stretch, etc. And in turn, because that specific bond absorbed a specific wavelength of light, we can in turn use this absorbance spectra to identify what functional groups are present in our molecule. Now, it's important to develop a mental model for bond vibrations, and the most common model is the ball and spring model. Vibrational frequencies can be predicted by modeling bonded atoms as a ball and spring system. For example, if you have like a carbon-hydrogen bond, you can imagine the two atoms as weights connected by a spring, where this spring is the bond between atoms. Now, if energy is added to the system, the bond and spring will vibrate with a defined frequency. So for example, if we add energy, then that bond will bend and stretch and this oscillation and this bending and stretching will occur with a defined frequency. So you can imagine as if I were to pull or start to move one of the atoms on this spring, and then I release that atom will move back and forth. This bond will bend and stretch, and that bending and stretching will occur at a defined frequency. Now, this can be connected to our atomic model in that as energy is added to the system, a transition occurs to a higher energy vibrational state. And this bond vibrational frequency depends on the mass of each atom and the bond strength and bond rigidity. With regards to the first factor, the mass of each atom, as the mass of bonded atoms increases, the frequency of vibration decreases. So for example, if we swap a hydrogen atom, which has a low mass, with a larger oxygen atom, we see that the vibrational frequency decreases considerably as atomic mass increases. The second factor, bond strength and rigidity, if we look at experimental data, stronger, more rigid bonds will have higher vibrational frequencies. The less degree of freedom your bond has, the more rigid your bond is, the higher the vibrational frequency, because the atoms have less freedom of motion in that bond. They can only really vibrate at a higher frequency. They cannot spread across a larger distance because the bond is shorter and more rigid. So stronger, more rigid bonds have higher vibrational frequencies. If you want to connect this to a mental model, if we had our spring made of metal versus if we made our spring out of a rubber band, the rubber band, because it's less rigid and can stretch farther, can vibrate at a lower frequency. If we had our band made out of metal, because it's more rigid, if we put energy into our system, it can only vibrate at a higher frequency. It can't stretch as much because the bond itself, the spring that's connecting our atoms, is more rigid. We can see this by the fact that if we go from a carbon-carbon single bond to a double bond, the frequency increases, and as we go to a triple bond, the frequency increases further. So the stronger and more rigid your bond, the higher its vibrational frequency. You can also see this in the difference between sp, sp2, and sp3 hybridized CH bond. Because these bonds have different strength, they have different vibrational frequencies. Because an sp-CH bond is the strongest, we can see it has the highest vibrational frequency. So, stronger, more rigid bonds have higher vibrational frequencies. The larger and heavier the atom connected to that bond, the lower the vibrational frequency. Let's now talk a little bit about peak intensity and peak width. So peak intensity depends on the change in bond dipole moment when the bond vibrates. Larger changes in bond dipole moment during vibration give a stronger peak intensity. In general, bonds with strong bond dipoles experience large changes in bond dipole during vibration and exhibit strong, sharp absorbances. For example, a CO bond is a highly polarized bond. So as it bends and stretches, you have a large dipole change. The reason why I'm specifically talking about the CO stretch is that the CO stretch is usually the most intense peak in the intense peak in the IR spectra due to the large bond dipole change. As you can see, for aldehydes, ketones, esters, and carboxylic acids, this very, very strong, very, very intense peak corresponds to the CO stretch. And it's often a signpost that you have a carbonyl present in your molecule. Peak width is pretty interesting in that peak width is often heavily affected by hydrogen bonding. Hydrogen bonding leads to broad OH and carboxylic acid OH peaks. So alcohols and carboxylic acids exhibit broad peaks as a result of hydrogen bonding, as hydrogen bonding affects the OH bond strength. In a large sample of molecules on the IR data collection timescale, a range of OH bond strengths are observed as molecules are rapidly engaging in hydrogen bonding. So hydrogen bonding in turn leads to broad peaks for alcohols and carboxylic acids. So alcohols and carboxylic acids exhibit a broad OH stretching peak. So here's the broad peak as shown here. For an alcohol, there's a specific feature of an alcohol where they exhibit a broad peak and they also exhibit a smaller sharp peak. So both parts of this peak correspond to the OH stretch. And the reason why this OH stretch peak is broad is as a result of hydrogen bonding. So alcohols and carboxylic acids exhibit this broad peak corresponding to the OH stretch. Let's now talk a little bit about the IR spectra in a holistic sense. So the IR spectra reports the percent transmittance or absorbance as a function of wave number. The absorbance depends on the change in bond dipole during vibration. The wave number depends on the specific bond, specifically the bonded atoms involved in that bond, and the bond strength. Each peak corresponds to a unique vibrational mode for a unique bond. So we can read out and identify the major peaks in a spectra, and in turn identify the major functional groups found in your compound. Now, I want to be very clear. In practice, infrared spectroscopy is used to deductively confirm or deny the presence of a functional group. Rather than checking for every functional group and trying to match the observed frequencies, it is often more efficient to identify the possible functional groups and check for their frequencies in the IR spectra. Here is a table of common IR absorption frequencies for different functional groups. Your goal is not to look at the spectra and then say, oh, I have this, this, and this functional group, but rather to say, based on my formula and based on my structure, I expect these functional groups, so I'm going to check for those peaks. So it's important to approach it deductively rather than inductively, in my opinion. Okay, so here's an appendix of the IR absorptions of common functional groups. We're going to be discussing the major functional groups in detail, but I wanted you to have this appendix reference. Here is a secondary appendix containing some of the other functional groups that are common in organic molecules. Now, let's now talk about the structural features in the IR for different compounds, and let's talk about what you need to look for in different compounds. So alcohols or carboxylic acids exhibit broad OH stretching peaks. The alcohol OH stretch is from 3400 to 3600, while the carboxylic acid OH stretch is a very broad peak at 3300. Now, how do you differentiate an alcohol and a carboxylic acid? There are two main features. The alcohol, you'll typically see a sharp peak adjacent to the OH stretch. This is also the OH stretch, but this is the sample of OH bonds that are not participating in hydrogen bonding. The second way to differentiate an alcohol and a carboxylic acid is that a carboxylic acid will have a CO stretch at approximately 1700. So alcohols and carboxylic acids exhibit broad OH stretching peaks. The alcohol will also have a concomitant sharp OH stretch peak, while carboxylic acids can be differentiated from alcohols because carboxylic acids will have the carbonyl CO stretch. Amines are pretty interesting in that amines, specifically if they have an NH group, exhibit a sharp, narrower NH stretching peak in 3,300 to 3,500 centimeters inverse. The 3,200 centimeter region and the 1,500 to 1,600 centimeter region is useful to indicate the presence of amines. The other thing that I'd like you to note is that primary amines and amides give two NH stretching signals. By comparison, secondary amines and amides give a single NH stretching signal. Not to state the obvious, but tertiary amines and amides do not have an NH stretch. The reason for that is if you look at this tertiary amine, there is no NH bond. So as we can see in this case, if we look at a primary amine, we see that we have 1, 2 peaks. Well, if we compare that to a secondary amine, we just see a single peak. The reason for that is for a primary amine, you can have both symmetric and asymmetric stretching. While for a secondary amine, there's no second NH bond. So you don't have as many unique vibrational modes. For an amide, as you can see, the primary amide has 1, 2 peaks, while the secondary amide just has 1 peak. Okay, so we talked about amines, amides, and carboxylic acids. Let's practice now, and I'd like you to tell me, in the following spectra, is the following molecule an alcohol or a carboxylic acid? So take a few moments, think about this very carefully, and then we'll discuss. So in this case, we see an OH stretch somewhere around 3,300 centimeters inverse, and I see this CO stretch at around 1,700 centimeters. So this, to me, looks like a carboxylic acid. Let's do another practice problem, and I'd like you to tell me, is the following molecule an alcohol or a carboxylic acid? Pause the video, take a few moments, and then we'll discuss. Okay, so here we have an OH stretch. This time it's closer to 3,400 centimeters, and we have an isolated OH stretching peak. So this tells me that we have an alcohol. The other thing I'd like you to note is that we have no CO stretch, so this can't be a carboxylic acid. Wonderful. Let's keep going now. Let's do some more practice. I'd like you to tell me, given a sample of 3 spectra, I'd like you to tell me which of the following spectra contains an alcohol, which of the following spectra contains an amine, and is the amine primary or secondary? Take a few moments to take a look at each of these spectra, and I'd like you to tell me, of these spectra, one of them corresponds to an alcohol, one of them corresponds to a primary amine, and the other corresponds to a secondary amine. And I'd like you to differentiate those spectra. So take a few moments, look at those spectra very carefully, and then we'll discuss. Okay, so let's take a look at this first spectra. So here we have an OH stretch, and we have a sharp OH stretch peak. We're at 1, 2, 3, around 3,400 centimeters inverse, and this is a broad peak. All of this supports the idea that we have an alcohol. This compound here, this spectra, matches that of an alcohol. Key signpost, broad peak, and this sharp non-hydrogen bonding OH peak. Looking at this second spectra, we're again around 3,400 centimeters, and we see 1, 2 peaks that are pretty close in terms of absorbance value. This matches the presence of an NH bond and specifically a primary amine because primary amines exhibit these 2 peaks in the 3,400 centimeter region. Looking at this last compound now, we just see 1 peak and it's close to around the 3,300 centimeter region. So I would expect this to be the secondary amine. The key thing that differentiates the secondary amine and the alcohol is that the alcohol peak is typically quite broad. It's relatively intense, and you have this side peak of the OH stretch for the non-hydrogen bonding OH bond. Okay, so we're able to differentiate alcohols, primary amines, and secondary amines. Let's keep going now. And let's talk a little bit about the IR spectra of alkanes, alkenes, and alkynes. So alkanes, alkenes, and alkynes have a characteristic CH stretch. The sp3 CH stretch is from 2850 to 2960, so less than 3,000 centimeters inverse. So for example, for hexane, the peaks are below the 3,000 centimeter line. Well, if we compare that to the sp2CH stretch, the sp2CH stretch is greater than 3,000 centimeters inverse at between 3,000 and 3,100 centimeters inverse, as we can see here. So this is the sp2CH stretch, which, as we can see, is on the left side that's greater than 3,000 centimeters inverse. Alkynes are usually very unique in that their SPCH stretch is around 3,300 centimeters inverse. So an alkyne is very easy to detect if it's a terminal alkyne. In terms of the carbon-carbon bond, alkenes have a carbon-carbon stretch in 1640 to 1680, which is right here. That's the CC stretch at 1640 centimeters inverse. And we can also verify that an alkene is present by virtue of the sp2CH stretch at around 3,100 centimeters inverse. Alkynes, unfortunately, have a weak CC stretch at 2,100 to 2,200. So the carbon-carbon triple bond stretch is around 2,100 centimeters inverse, but you may not always see it. So always look for the SPCH stretch at around 3,300 centimeters inverse. So we can differentiate alkanes, alkenes, and alkynes based on the CH stretch and confirm an alkene or alkyne using the carbon-carbon double bond or triple bond stretch, respectively. Let's do some practice now, and let's identify if the following spectra contains an alkane, an alkene, or an alkyne. So pause the video, take a few moments to work through this example, and then we'll discuss. Make sure, as instructed by the problem, to circle the peaks that you're using to justify your assignment. Okay, so first and foremost, here is a peak at about 1650 centimeters inverse. This is a carbon-carbon double bond stretch. And we have a peak at about 3100 centimeters inverse, which corresponds to an sp2ch stretch. So this supports an assignment that this spectra indicates that the compound, it contains an alkene. Let's look at another spectra now. So I'd like you to take a look at the following spectra and tell me if we have an alkane, an alkene, or an alkyne. So pause the video, work through this example, and then we'll discuss. Okay, so in this case, we have a peak at about 2100 centimeters inverse. This matches a carbon-carbon triple bond stretch. And we have a pretty unique and intense peak at 1, 2, 3, about 3400 centimeters inverse. Actually, 1, 2, 3, that's 3300. That corresponds to an SPCH, which suggests an alkyne is present. Specifically, a terminal alkyne, because we see the SPCH bond stretch in the spectra. Okay, let's keep going now, and let's do some additional practice. This time, we're looking at one pretty important application of infrared spectroscopy, which is to verify whether a reaction has gone to completion. So in this case, a researcher treats cyclohexene with osmium tetroxide, followed by sodium hydrogen sulfide. So in this case, they're dihydroxylating the alkene to make a diol. So I'd like you to tell me which of the following spectra matches the reactant cyclohexene and what spectra matches the product diol. And I'd like you to identify the peaks in each spectra to support your conclusion. So here are the two spectra. I'd like you to take a look at each of these spectra. So pause the video, work through these examples. So here's the first spectra. Here's the second spectra. And I'd like you to tell me which spectra corresponds to cyclohexene and which spectra corresponds to 1,2-cyclohexane diol. So pause the video, work through this example, and then we'll discuss. Okay, so first and foremost, I see here this pretty characteristic set of peaks at around 3,300 centimeters inverse. So this suggests to me the OH stretch. So I suspect this top spectra corresponds to the cyclohexane diol. The bottom spectra, in this case, we have a peak at around 3,100 centimeters inverse, which corresponds to the sp2ch stretch. And we see a peak at about 1650 centimeters inverse, which corresponds to the CC stretch. So this second spectra matches cyclohexene. So as you can see, we can use IR to differentiate between the reactants and products of a reaction. For those curious, these IR spectra were obtained from a literature spectra database. And if you collected a spectra yourself on an IR spectra, such as those that we have in the lab, you would see a spectra that looks pretty much identical to the ones that we're analyzing right now. Okay, let's talk a little bit about the IR spectra of aromatic compounds. So aromatic compounds have three major peak groups. The aromatic sp2CH stretch around 3030. Another signpost that you have an aromatic compound is you may only see CH peaks above 3000 if no alkyl groups are present. Aromatic compounds also exhibit weak peaks from 1600 to 2000 and medium intensity peaks from 1450 to 1600. These are mostly the CC stretching and stretching absorbance frequencies. One thing that's very unique for aromatic compounds are the out-of-plane bend peaks in the 1650 to 900 centimeter region that are unique for substituted aromatic rings. Here is a table that indicates the various substitution patterns for the out-of-plane bend peaks for different substitution patterns for aromatic rings. In the event that you have to differentiate a set of aromatic compounds and the aromatic compounds have differences in substitution, you can actually differentiate aromatic compounds based on their substitution pattern using the out-of-plane bend peaks. So, for example, from the IR spectra, we can see that toluene is an aromatic ring and it's monosubstituted because it contains out-of-plane bend peaks matching the monosubstituted pattern, where if it's monosubstituted, you'd expect to see 1, 2 peaks in the 600 and 700 region. Okay, let's continue on now and discuss another very important functional group, which is the carbonyl functional group. And let's talk about the IR spectra of ketones, aldehydes, and esters. The CO stretch is a very intense narrow peak centered around 1700. Aldehydes have a characteristic CH stretch at 2800 to 2860 and a CO stretch at 1730. Conjugated aldehydes appear at 30 centimeters at an absorbance value that's 30 centimeters lower at around 1700 centimeters inverse. That's because conjugation weakens your CO bond and leads to a lower CO bond stretching frequency. So for aldehydes, you can use both the CO stretch, which is around 1730 if it's non-conjugated and 1700 if it's conjugated, and you can check for the CH stretch at around 2800 centimeters inverse. The ketone CO stretch is at around 1715 in a six-membered ring and for acyclic ketones. It's around 1750 in five-membered ring ketones and 1690 for ketones that are conjugated to a double bond or an aromatic ring. So generally, whenever you have conjugation, just subtract 30 from the absorbance value. Lastly, the ester CO stretch is around 1735 if it's saturated and 1715 for conjugated esters that are conjugated to an aromatic ring or a double bond. So, as we can see, comparing our CO stretch absorbance values, we see that the general ranking and hierarchy is ketones, followed by aldehydes, followed by esters, with esters having the highest stretching frequency values and ketones having the lowest. So let's practice identifying and differentiating ketones, esters, and aldehydes. So in this case, we have 3 spectra provided, and I'd like you to tell me which of the spectra contains a ketone, which spectra contains an aldehyde, and which spectra contains an ester. So take a few moments, take a look at these 3 spectra, and then we will discuss. As a reminder, in terms of wave number values, as we've discussed, we have aldehydes with the lowest, followed by ketones, followed by esters, which are the highest. Aldehydes also have the CH stretch at 2800 centimeters inverse. So aldehydes are around, before you work on this problem, let me just list them out just for your reference. Sorry, it should be ketones, then aldehydes. Ketones around 1715, aldehydes are 1730, and esters are 1735, with aldehydes having the CH stretch at 2800. So, with that information in mind, I'd like you to tell me for each of these spectra, which spectra contains the ketone, which spectra contains the aldehyde, and which spectra contains the ester. So pause the video, take a few moments to work through this example, and then we'll discuss. Okay, so first and foremost, this stands out to me. These peaks around 2800 centimeters inverse are a signpost for an aldehyde. I'm also going to draw a vertical line from the center of each peak, just to help us compare. Okay, so as we see, spectra A and B have pretty close CO stretching frequencies. Let's trace this down a little bit further. Okay, so I'm going to tentatively assign this first spectra to the aldehyde because it contains these CH stretches, and it looks like we're pretty close to around 1730. Looking at the second spectra, I'm just going to erase this guideline that I made. And just as we can see, of the remaining spectra, one corresponds to the ketone and the other corresponds to the ester. So we're essentially looking for whatever peak it has the largest wave number value, and that's likely going to be the ester. So in this case, looking at this last spectra here, I'm going to zoom out so that way we can see all of the spectra on the same page. And as we can see, let me use a ruler. Let's see which peak is farthest to the right. So we have our aldehyde. And as we can see very clearly, peak C is the farthest to the left, and it has the highest absorbance value. So I'm going to tentatively assign peak C to be my ester, and peak B I'm going to tentatively assign to be the ketone. One thing that makes differentiating between ketones, esters, and aldehydes relatively difficult is that the absorbance values are pretty close. In this case, the way that I differentiated the aldehyde from the ketone and the ester is the presence of these very sharp CH absorbance values that are only present in the aldehyde. Okay, so with that, we were able to differentiate between a compound containing a ketone, an ester, and an aldehyde. Let's do some additional practice and let's talk a little bit about the difference between conjugated and non-conjugated ketones. So in this case, you're provided the spectra for a conjugated and non-conjugated ketone, and I'd like to assign each compound to the matching spectra. So we have two compounds that I'll tentatively label A and B, and I'd like you to tell me from these two spectra that are provided below, which spectra corresponds to which compound. So take a few moments to work through this example, and then we'll discuss. So first and foremost, if we compare these two spectra, the one thing that immediately stands out to me is that in this bottom spectra, we have a peak around 1600, which corresponds to a CC stretch, and then we have our CO stretch. As we can see, if this peak is around 1730, or if this peak is around like 1720, this peak is closer to 1700 centimeters inverse for the CO stretch. So, given these two pieces of information, one, the presence of a CC double bond, which is required for it to be conjugated, and two, the fact the CO absorbance value, the CO stretching value is lower frequency, this tells me that this spectra matches the conjugated ketone. In other words, it matches structure B. While this top structure with a higher frequency CO stretch and no CC stretch matches structure A. So as you can see, we can differentiate between conjugated and non-conjugated ketones using the CO stretching value. Okay, let's talk about one other set of functional groups, which are alkynes and nitriles. So this is the last major functional group. Triple bonds have an absorbance in the 2050 to 2250 centimeter region. The nitrile CN stretch is from 2200 to 2300, while the alkyne CC stretch is from 2100 to 2200. The CC stretch for alkynes is often very weak. So here are examples of alkynes versus nitriles. As you can see, the carbon-carbon triple bond stretch in an alkyne is very weak, and you may not even see it. The last thing I'd like you to note is that internal and terminal alkynes can be distinguished by the SPCH stretch. So for example, as you can see in blue, if you have a terminal alkyne, you'll see the SPCH stretch at approximately 3,300 centimeters inverse. If your alkyne is internal, there's no CH stretch because there's no alkyne SPCH bond. One thing I'd also like you to note is that one easy way to compare IR spectra is to physically take the pieces of paper, overlay them, and hold them up to the light, and you'll be able to see the difference between the spectra based on which peaks don't line up compared to the before and after. Okay, so that concludes our discussion of infrared spectroscopy. It's a really powerful tool for identifying functional groups, and it's a complementary tool to mass spectrometry and to the next structural method that we'll be discussing in the next chapter lecture, which is NMR spectroscopy. So with that, this concludes our Chapter 10 lecture. The next lecture series will focus on Chapter 11, which discusses NMR spectroscopy.